All right, all right, all right. Good afternoon. Let's everybody calm down. I'm glad to see everybody's having fun for a Friday afternoon. Let me see what I can do to change that. No, I'm just kidding. I'm just kidding. It's just a subject that we're looking into. All right, let's see. Where did we stop last time? No, not there. That one. Okay. All right. 306, page 9. Then let's move on to the next. All right, everybody, let's focus. So we stopped here. We were looking at the diode IV curves, and we spoke about, everybody, let's calm down. Could always turn on some music and have a party. And then we can have a surprise quiz on Monday. Well, surprise would be that everything that we're supposed to do today would just be student reading. Okay. All right. So IV characteristics, we were talking about how the diode is a nonlinear device. So once we apply a diode biasing voltage across its terminals, it does not turn on because there is a junction barrier in between, known as the depletion region. As the voltage increases, we start seeing some effects where carriers are now pushed towards the junction, so they're able to cross over. So slowly and steadily, the current starts increasing when the voltage is increased. Okay. After a certain point, we reach a sharp turn. There, the current increases rapidly after a certain point. So the depletion region barrier is completely overcome, and now there's a rapid influx of charge carriers crossing the junction. Holes from the P side and electrons from the N side are now able to cross over the junction. Current starts flowing in that diode. This is known as the turn on voltage. It's also known as the knee voltage. So that's not used typically. But if you ever read or hear the words knee voltage with regards to a diode, that's what it's referring to. These voltages are very well categorized. It's not categorized, sorry. Very well characterized. For silicon, it's between 0.6 to 0.7 volts. For germanium, it's 0.2 to 0.3 volts. Gallium arsenide is somewhere above 1.2 to 1.3 volts. Okay. And I'm assuming at this point, everybody is done with lab 3, right? So if you did the experiment with the regular silicon diodes and with the LED, what difference did you notice? Something. What if I said there was no difference? You don't remember? Nobody remembers. What come up in the lab exam? Well, the difference is staring right at you on the screen. Turn on voltage for gallium arsenide is 1.2 volts. LEDs are compound semiconductors made from gallium. And the different colors of the LEDs result from the different impurity dopants that we use. So LEDs to turn on required more than 1 volt. Well, it actually required more than 1.2 volts. So that was the difference. Okay. So when we use the silicon diodes, we use sweep and go. Did everybody use sweep and go in the other labs also? Yes, no? At least I know in my labs it worked. Fine, okay, great. So sweep and go is a great software. Now you can compare and contrast how long it took to take the manual characteristics versus an automated one. Right? So with the LEDs, requires more than 1.2 because the barrier, the depletion region is slightly wider. All right. And on the reverse side, of course, this is, let me note this down here. This is forward bias, and this is reverse bias or reverse mode of operation. This is the origin, 0, 0. Diode characteristic always passes through the origin. 0 volts, 0 current. Okay, 0 volts will always result in 0 current. So it always passes through the origin. And that is also something we would have observed when we did sweep and go reverse bias and we zoomed into the characteristic. It began at 0. And also in the PSpice lab, where we simulated and put it on the log scale, you would have seen the current y-axis. Current on the y-axis was compressed scale, and so you were able to see it pass through the origin. Okay. This is the diode equation. One equation to rule them all. You'll see this equation again and again and again. Okay. So ID is diode current. VD is diode voltage. There's one term missing in there. Need to have Q. And then the exponent shows you the exponential relationship between the voltage and the current. All right, so let's break it down. What do we have? ID is the diode current. Diode current is exponential in relationship to the applied diode voltage. And we can see that from the E. IS is the saturation current. This indicates saturation current is a result of minority carriers. Because the minority carriers are very low in number, the resulting current due to their movement is also very low. And so saturation current, IS, is typically in nanoamps or less. Okay, and it's a function of device manufacturing. We can design devices that have some specific amount of saturation current. Sometimes it's also known as the reverse leakage current. Okay, reverse leakage current. And you will encounter these in many forms in different semiconductor devices. So that's the saturation current. There should be Q right here in the numerator. I've been meaning to fix this in my original PowerPoint for like a year now, and I keep forgetting every time. There should be a Q in there. Canvas does. The PDFs. Okay, that means I fixed it, but I never fixed these. Okay, so Q is the unit charge. That's a constant. And then N is the well, actually, let's keep the N away from now. K, what is K? I already wrote the B. This is directly from the thermal voltage. Okay, so we'll reduce the function in just a minute. And then T is the temperature in Kelvin. And I don't know about the other labs, but in my lab, we also ran a PSpice simulation for the diode voltage as a function of temperature. So does anyone remember what happened when we ran that simulation? What happened with increasing temperature? Voltage kept decreasing. Does the equation make sense? Can we relate those results with this equation? Not yet, because voltage is on one side, but we will in the next couple of slides. And then let's come to N. N is a non-ideality factor. This is again provided by the manufacturer. It simply indicates how nonlinear this device is. Typically, it's between 1 and 2 or 1 or 2. For most diodes, we simply take it as 1. Okay. Just as an exercise, you might sometimes give it 1.1 or 1.2, but for most regular silicon diodes, we simply take n is equal to 1. Thermal voltage, if you remember from chapter 2, is kT over Q. So now let's simplify this equation. What do we have? If n is equal to 1, we can remove that. We can reduce this expression, ID equals the saturation current times E raised to VD over VT. And that's it. For most cases, we can use this approximation. Diode current ID is directly proportional to the exponent E raised to VD. So good question. What about that -1? For most cases, this term right here will be far larger than 1, and we can ignore that 1. Not if you want the most accurate answers, we will not ignore it. But if you want an approximation, then let me put that approximation sign. So it's approximately equal to IS times E raised to VD over VT. Semiconductor analysis is all based on numerical methods. So we always use approximations and assumptions. We make an assumption, we perform our calculation, we look at the results, we see if the results match up with our assumption. Yes, then we can end the process. No, then we go back to the top, make another assumption, and redo our process, redo our calculations. So for most, sorry, it's just not always possible because these devices. So the question being asked is, why don't we just have a fixed equation? And the answer is just the nature of physics, nature of these devices. There are so many factors affecting these devices that no single model, no single equation is able to accurately capture all environmental conditions. Even something as basic as Ohm's law, which we say applies to all resistive circuits, but caveat is it only applies within normal operating conditions. Right? If the pressure is extreme, as the temperature is extreme, then Ohm's law also no longer applies. But we don't really, look at that in most of our basic classes. Okay, all right. So let's look at what happens for diodes under 3 different conditions. We can apply a positive voltage to the anode, negative to the cathode. That is known as the forward bias. That's on the next page. If it'll ever load. I don't know. It never used to do this before. This is the first quarter it's doing this. That's zero bias. That should be reverse bias. And then this is forward bias. All right, so in forward bias or forward mode of operation, we are applying positive voltage to the p-type material, negative voltage to the n-type. If we flip that, we apply negative to the p-type and positive to the n-type. We call it reverse mode of operation or reverse bias. And then if we don't apply anything, that is known as zero bias. Bias, by the way, simply refers to the process or the act of applying external DC voltage. Okay. We are simply setting up our device to operate within some constraints. That's what we're doing. That's what biasing means. Okay. This is the word that you will use again and again and again. You will encounter again and again going forward. Okay. That's what biasing is. And more often than not, it always refers to applying a DC voltage or current. We are forcing our device to operate within a certain range. So that's bias. So zero bias, as the name suggests, we are not applying any external energy source on our device. We simply take our device and it's sitting on our table, right? The wafers that we passed around, they had diodes in them, the cal poly wafers. They had cal poly diodes. They were PN junctions under zero bias. So they were at equilibrium. So they were at thermal equilibrium, meaning there is no flow of charge, and hence there is no current flow in that circuit. It just exists. Okay, it's not positively charged, not negatively charged. Charge neutrality equation always applies. And so under zero bias, there is nothing. There is phi j present, which is the junction potential, right? And so junction potential exists. Depletion region exists. And thus phi j, the junction potential, also exists. There's no way to overcome it without external energy. Okay. Now, of course, we have seen this in the simulations in the lab. We also perform experiments this week, and you were able to see when you didn't have enough current or enough voltage being applied to the diode, there was no resulting flow. Once voltage started increasing, forward bias is the process of applying positive to P-type, negative to N-type. And so at that point, what is happening? I had the two slides in reverse. I should have had forward first. Anyway, so what happens? Let's just draw it out. Okay, that's too far apart. Let's just make it closer. Somebody on Zoom, please send a message. Thank you. All right, so we have positively charged holes and negatively charged electrons on either side of this junction. What happens when you have positive voltage going there? Holes are pushed towards the junction. Electrons are again pushed towards the junction from the other side. So the depletion region starts to shrink. The charge carriers are absorbing more energy. Because they have energy, they're able to flow across the junction. Depletion region shrinks, and because it shrinks, now current can start flowing once that barrier is overcome. Current flow is described as flowing in this direction. And so through the PN junction, it's moving from the anode to the cathode. Okay, moving in direction of the holes, opposite of the flow of electrons. Okay. So until that junction barrier is overcome, there is no current flow. But once it's overcome, there's a heavy influx of carriers. And now we have exponential increase in the current for a very small increase in the voltage. And this is known as the forward mode of operation. Hence, forward bias and forward current. Okay. And this is the most common form of common mode of application for diodes, regular silicon diodes. This is a very important property because this property is what allows us to convert AC to DC. It only conducts in one direction. The reverse direction, we have nothing. Just the reverse saturation current. Speaking of which, let's look at the reverse bias. So in reverse bias, we are flipping the sign of the applied voltage. So I'm going to be lazy a little bit. I'm going to simply copy this. All right, so in this case now, we have negative, we have positive. What is happening is the holes are attracted away from the junction, so are the electrons. And because they are being attracted away, this depletion region is going to increase. Okay, the depletion region width keeps on increasing because the charge carriers are being pulled away. And there are several effects that occur over here which have real life applications. So we'll talk about those also. But the depletion, the main point here is that when you reverse bias a PN junction, the depletion region is going to increase, and the only current that flows in that reverse mode of operation is the reverse saturation current IS. And the reason because that occurs is because there are minority charge carriers present on both sides of the junction. So in the N side, we have minority carriers holes which are positively charged. On the P side, we have minority carriers which are electrons which are negatively charged. So the same effect that we looked at in the forward bias will occur with the minority carriers in reverse bias. The holes in P-type, which are very small in number, are pushed towards the junction, and the electrons, which are on the N side, which are again very small in number, are also pushed towards the junction. And they are the only ones that will cross through that barrier. Hence, results in a small, very, very small current known as IS. Okay, that's known as IS. All right, let's take a pause. Let me know if you have any questions. Okay. These are the, well, not, these are the equations that we can, well, not these are the equations. This is the equation, the Diode equation that we can apply to determine the current or just prove what current exists for each mode of operation. Okay. Kind of self-explanatory, but I'll just let you look at it before I begin explaining. What do we see? Mathematically, we can see it's IS 0, and of course has some value, right? Physically, we just spoke about what's happening physically at the junction. Let's look at zero bias first. With zero bias, what do we have? What happens to this term? It's to 0. So 1 minus 1 equal to 0. This is the instant where we do not neglect that minus 1. Okay. So in this case, if we neglect the -1, then our answer would be incorrect. But this is the instance where we do not neglect that -1. So zero bias, zero current. Negative voltage, this exponential term is going to become negligible. And again, we approximate it with 0, 0 minus 1, end result being minus IS, reverse direction, reverse leakage current IS. Okay. And then finally, forward bias. Forward bias, the same, depending on our application, depending on what we want. We can approximate it by ignoring a few things, or we can have all of the factors in there. And then in forward bias, we have the forward diode current. Okay, yes. So question being asked is the saturation current different for different diodes? The answer is yes. Saturation current is a result of the manufacturing process, meaning it's dependent on the doping, which means it's dependent on the dosage that is chosen by the manufacturer or the circuit designer. So we think we calculated a few years ago, like, the diodes that we fabricate here in the cleanroom class at Cal Poly. We know what the dosage is approximately, and the process is characterized, so we can kind of predict what the saturation current is. But here's the thing with semiconductor devices. Even if you take the exact same device, built and manufactured at the exact same time, on the exact same die, side by side, right down to the microsecond, it still is impossible to have two exactly identical devices. It's impossible. So no two diodes or no two transistors will ever be alike, even if they are manufactured at the exact same time. There's only a range of applications, range of values where it'll have similarities. But right down to the smallest micro or nanoamp characteristic, it's never possible. Simple reason being, because we are talking about atoms and subatomic particles in the range of 10 raised to 18, 10 raised to 19. It's a huge, unimaginably long number. We cannot control our doping or process down to the single most atom or electron. As simple as that. We can control it up to a certain level, but beyond that, we have no control. But that's still good enough to create modern day semiconductor devices. Okay, so keep that important point in mind. No two semiconductor devices will ever be the same. Okay, any other questions? Okay. So diode temperature coefficient. Let's look at what happens when we reverse or flip the equation to determine diode voltage if we are given diode current. Right? ID was directly proportional to the exponent of the voltage. Right? So you simply flip it on the other side. Take natural log of ID after transfer all the other quantities on the other side, and we obtain diode voltage is a function of VT and ID. Okay. The important takeaway from this equation, though, is that diode voltage is a direct proportional to thermal voltage, VT. And thermal voltage is KT over Q. K and Q are constants. Therefore, diode voltage is directly proportional to temperature. And the relationship is very well categorized. And this change in diode voltage as a function of temperature is very linear. Okay. It's approximately 1.82 millivolts decrease for any decrease in temperature. Okay. And so there is an example in the book of a real life application. Because the semiconductor devices have a linear relationship with temperature, we can use it for temperature sensing. One of the most popular is digital thermometers. So any kind of digital thermometer that we use nowadays has a diode circuit built in. So in the book, there is an example. Please review that example in the book. Okay. Okay, so now let's talk about the effects of what occurs when it's reverse bias. We talked about what happens in forward bias, right? So forward bias is depletion region shrinks. Because it shrinks, we can now have forward current flowing through it. And then later on, we'll look at what applications we can apply that process to. But now let's look at reverse bias. If you look at reverse bias, what is actually happening? And it's very interesting. We said that the depletion region increases. What is happening is it's increasing in both direction, right? So the space charge region is increasing. The electric field that is now being created in there is also increasing. This is an important point. The electric field also increases. Everything is increasing. So depletion region width increases, everything increases. The electrostatic potential also increases. VR here, by the way, simply the reverse voltage. Okay, by how much it's increasing. So the original junction potential is now increasing, and that increase is characterized as VR. That's the voltage that we're applying over there in reverse bias. So it increases the built-in potential, increases WD0. But it's not an ideal situation, right? It's not an ideal device. So there is a limit on what will happen. So what happens are two effects. First effect is this. What happens when the electric potential increases? Remember, when P and N type form a junction together, holes and electrons start diffusing. When they start diffusing, it generates an electric field. That electric field is in opposition to that original diffusion, so it stops the diffusion. But now that space charge region is increasing. If that space charge region is increasing, meaning the electrons and holes are being pulled away from the junction, what is being left behind? More ionized atoms. And that's the reason why the junction region or the depletion region is increasing. So more ionized atoms are being left behind in that space. The space charge region is increasing. And because that space charge region is increasing, that electric field is increasing. And at some point, that electric field is going to impart some energy to the fixed in place electrons and atoms. Okay. And when that happens, after a certain point, it results in breakdown of that junction. And because it's in reverse bias, it's known as the reverse breakdown. Okay, reverse breakdown. This is something that we'll do next week. We'll have applications of diodes, diode rectifier circuits, and we'll also look at Zener diodes. So reverse breakdown, let's take a look at what reverse breakdown is. This is forward bias right here. Actually, let's do it this way. Forward bias, reverse bias. Reverse bias simply means you're applying positive voltage to the cathode. Okay. So up to this point, what we have is the reverse saturation current, IS. Right? There's no other current. It's only the reverse saturation current, IS. But let's say it reaches a certain point. Now, at that point, what was noticed was the sudden influx of carriers and a huge amount of current started flowing through. This slope, by the way, is highly exaggerated. Okay, highly exaggerated. Actually, I forgot my G. That slope is even steeper. It's almost like a straight line facing vertically downwards. The current increases, voltage remains at a near constant. Okay, and this is known as a Zener effect. Zener effect. So let's write those down. Almost a straight line. So what is happening? There are actually two processes that are happening. There's a Zener breakdown, and there's something known as avalanche breakdown. Okay, Zener breakdown typically occurs for voltages of 5.6 volts or less. Avalanche breakdown occurs for voltages greater than 5.6 volts. There are two distinct and separate mechanisms. Okay, in Zener breakdown, what is happening is we have heavily doped junctions. Okay, so there's heavy doping on both sides. So there are already a lot of minority carriers, a lot of carriers present at the junction. So when you apply reverse bias, what is happening is these heavily doped charge carriers, they automatically receive enough energy or sufficient energy that they're able to actually cross over the barrier. So they're directly able to tunnel through, sort of, going from the conduction band, valence band into the conduction band. All right. And so that effect is observed in only heavily doped devices, typically below 5.6 volts. And then there is something known as avalanche effect. Okay, avalanche effect. Not as sinister as it sounds. What happens in avalanche effect is that the application of an external electrical field, which is increasing in strength, it imparts enough energy to many of these electrons that they are ripped from their bonds and they are now free to move around, okay, inside the depletion region. So you're applying a reverse bias. That reverse bias is an external electric field. When you apply a high electric field density across a very small region, it imparts sufficient energy to some of the charge carriers in there that they're able to break free of their bonds and are now free and available for conduction. Now, these are acted upon by these electric fields, and so they are pushed towards the junction, so they cross over, and they are moving haphazardly or randomly in the lattice structure, but they're moving with high energy. And when that happens, they're going to strike other atoms that are present in the structure, thereby dislodging more charge carriers. And those free charge carriers are now going to impact, they're going to be acted upon by electric field. They result in more collisions, more charge carriers. Hence, it results in a cascading effect or an avalanche effect, where 1 goes into 2, 2 multiplies by 4, 4, 8, and so on and so forth. And then there's a sudden influx of these charge carriers, and they all cross over the junction because of this applied electric field. And this is known as the impact ionization. Electrons are impacting the atoms, creating more ionized atoms. More charge carriers are generated. More charge carriers are generated. They result in more energy being fed from the electric field. And thus, it results in an avalanche of charge carriers crossing through the junction. And that is known as the avalanche effect. Okay, so there's the Zener effect or Zener mechanism, and there's the avalanche mechanism. This is for less than 5.6 volts. This is for greater than 5.6 volts. This is a result, Zener effect is a result of heavy doping. And this is a result, avalanche is a result of, since I used the word heavy, let me use the word heavy again, heavy reverse bias. In the process, known as impact ionization. Impact ionization. The thing that happens because of heavy doping is that the depletion region is thin. Okay. Let's take a pause. Let me know if you have any questions. Any questions? Reading assignments are already posted online, so please keep up with your reading. That definitely will help in understanding the material. Okay. We're almost at the end of semiconductor physics. From here onwards, we'll be going into circuits and circuit analysis. Okay. Questions? All right. So everybody understood everything? If I ask you to explain it back. All right. One thing to keep in mind is that for some reason, convention is that if you operate a device in reverse breakdown mode, they're all referred to as Zener diodes. Whether it's for less than 5.6 or greater than 5.6, they're all referred to as Zener diodes. We can buy Zener diodes that are heavily doped, going all the way down to 2 or 3 volts, all the way into hundreds of volts. Okay. The big property of Zener diodes is that they are used exclusively in reverse bias because they function in reverse bias, meaning they are completely off until their reverse breakdown voltage is reached. And once their reverse breakdown voltage is reached, they hold the voltage constant across itself, but can withstand large amounts of current. So they can divert large amounts of current through them while keeping the voltage across their terminals constant. And that is the big application of Zener diodes. Okay. And that's why we use them for like voltage regulation, to keeping output voltages constant. Okay. Let's see, we have about 4 minutes left, so 3 minutes. Reverse bias, there were some properties or circuit analysis. So one more left. All right, diode capacitance. Remember, I think I did mention this, right, in class, because we have the space charge region. The space charge region is storing some charge in there. especially in reverse bias. When the depletion region is increasing, it's now storing more charge. And so we can define a couple of quantities in there based on the stored charge. And both of them are referred to as diode capacitance. So diode capacitance in reverse bias is known as junction or transition capacitance, CJ. And in forward bias is known as the diffusion capacitance, CD. Equations for both are listed right here. Here, these terms are already familiar, ID and VT. Tau T is the transit time of a charge carrier. Okay, transit time. CJ0 here, phi j is the barrier potential, VR is the reverse bias applied voltage. CJ0 is the junction capacitance 0. So, means zero bias. So CJ0 is epsilon A or WD0. That's the junction width. Okay. A couple of minutes left. I can explain this a little bit quickly. I brought up the capacitance equation. Anybody remember? C is equal to epsilon A over D, right? So how does it translate? Well, PN junction, the fabrication, looking at it from the top, what do we have? We have a, let's just say it's a large rectangle. Let's say it's N type. Doesn't really matter whether it's N or P type, but we have a structure and then we implant a different structure in there. This is from the top, looking at it from the top. How about if you look at it from the side? What do we see? And of course, the dimensions are completely exaggerated. Right? We have this N-type structure, and we implant a P-type structure inside it. So it's going to be like this. Right? And the PN junction exists right here, where they meet up. So it's like right here. It's very, very, very thin. So it's completely, again, exaggerated. It's right there at the border where the P and N type meet up. Okay. So now there is charge that is stored in that junction. Okay. Charge that is stored in that junction. What is the width of that junction? WD0. So that is the separation between the two plates. Okay. So WD0 defines a separation between the two plates. Cross-sectional area A is basically the physical dimensions of the structure. So this is A area. And the distance between the two plates is WD0. Hence, capacitance in that PN junction, which is epsilon A over D, is the cross-section of the physical structure of that device divided by the junction depletion region width. Yes. Sorry, which? What kind of diode? Transient voltage suppressor diode. I haven't heard that term in a while. Does it have what? Transient voltage suppressor. No, that might be a Zener diode. Is that you are using it, what? So yeah, transient voltage is like, there's a voltage coming in, there might be a spike. And to get rid of those spikes, I mean, we would suppress the spike. So suppressor diode brings a Zener diode to mind. These diodes are known as, so there are diodes that are specifically manufactured so that we can use them as voltage controlled capacitance or capacitors. So voltage controlled capacitor, hence variable capacitor, hence the term varactor diodes. Okay, varactor diodes. Okay, it's already 4:02, so we're in a couple of minutes over time. We'll end class here today. Quiz on Monday based on the topics we have covered so far. So keep up with the reading. There might be some short answer questions and definitely using one or two problems based on the equations. Okay. So I'll have a good weekend and I will see you all on Monday. All right.